Hello again, Physics 20s. In today's lesson, we are going to wrap up Physics 20 in terms of content by talking about the Doppler effect, where our learning outcome is to explain qualitatively and quantitatively the Doppler effect on a stationary observer of a moving source. Okay, I have a really poorly sketched diagram at the bottom of the page, which I'll get into in just a moment. Okay, so first of all, we're going to look at an observation made by a scientist of the name Christian Johann Doppler. And what he noticed is that there is a difference between the actual frequency emitted from a star and the frequency observed by a person. Now, the frequency we're talking about in this situation is the frequency of light that's being emitted by a star. And what was noticed is, so we're going to call the star the source of my light. And we're going to call the Earth the receiver. We'll say the receiver or the observer. So what I've done is I've drawn the picture of the Earth, and I have a person looking through a telescope observing the star. So this person could be like Doppler. And light has a specific frequency to it. Now, just to kind of talk about the frequency of visible light, we're going to look at the continuous spectra of color. So for the continuous spectra of color, what we have is we have the colors red, orange, yellow, green, blue, indigo, and violet. Now, if we organize this in terms of wavelength, red light has a wavelength that's somewhere around 700 nanometers. Violet light has a wavelength that's somewhere around 400 nanometers. So that's the wavelength range from visible light. It's about 400 to 700 nanometers. So if we go from red to violet, the red would have the higher wavelength, and the violet would have the lower wavelength. Now, we're not talking about wavelength here. Specifically, Doppler is talking about the observed frequency. So let's look at how the frequency would compare. Well, to determine frequency, look at the universal wave equations. The universal wave equation tells me that V is equal to F times the wavelength. If we manipulate for the frequency would be equal to V over lambda. Now, if V is a constant, which it is for light in a medium, it moves at around 3.00 times 10 to the 8 meters per second, I can just look at an inverse relationship between the frequency and the wavelength, which means that if the wavelength is big, the frequency is going to be lower. So red light would have a lower frequency and violet light would have a higher frequency. Okay, so this star is emitting, now it's not a mechanical wave, it would be an electromagnetic wave because it crosses empty space. It doesn't require a medium to travel through. So it's emitting light with a particular frequency. Now, what Doppler noticed is that depending on whether the star is moving towards the Earth or it's moving away from the Earth, that frequency is going to be a little bit different. So let's say that, for example, I'll make up a fake number. Let's say that the star emitted a frequency of light of 400 hertz. By no means is it this frequency, okay? 400 hertz. So that's if the Earth and the star are stationary. But he noticed that if the star is if the Earth is in its orbit where it's moving towards this star, then the observed frequency is a little bit different. So maybe it's like 410 hertz. Or if the Earth is moving away from that star, they notice that the observed frequency of the star is actually 390 hertz. So there's some kind of connection here between the relative motion between the Earth and the star in comparison to whether the star is moving towards or away from the Earth. And depending on whether it's moving towards or away from the Earth, the frequency is going to be a little bit different. Now, we have different words that can be used to describe this. If we have a situation where the star is moving towards the observer or towards the Earth, we refer to that as being a blue shift. Okay, so in this situation, so if it's moving towards the Earth, we call this blue shift. Now, this doesn't mean that the star is going to appear blue in color if it's moving towards the Earth. It just means it shifts towards the blue part of the spectrum. Okay, so what color is the star initially? The star, if there's no relative motion between the Earth and the star, is green. Well, if the star is moving towards the Earth, it would shift towards the blue part of the spectrum. So it could appear either blue, it could appear indigo, or it could appear violet. So in this situation right here, we'll just say that it appears blue. So it just makes a small shift over to blue. Now, if we have the star or relative motion in a way so that the Earth and the star are moving away from each other, we refer to that as a red shift. Again, a red shift does not mean that the star is going to appear red in color. It just means that the color of the star is going to shift towards the red end of the spectrum. So it might shift to yellow, orange, or red. So maybe in this situation, the star would appear, let's just pick this one, orange in color perhaps, okay? A lot of it depends on how fast they are moving relative to each other. Okay, so we'll say it appears orange. Not that you can see that because the font color is pretty bright there. Okay, so that's called red shift. So blue shift is the relative motion would be the stars moving towards the observer, or the red shift would be the stars moving away from the observer. So depending on relative motion, there's a difference in the frequency. And it turns out this is what we refer to as the Doppler effect. Now, we're not going to worry about this for an electromagnetic wave. Electromagnetic waves are reserved for physics 30. So we're going to look at this in terms of an application to a mechanical wave, specifically with sound. We know sound is a longitudinal wave where the particles in the medium vibrate in a direction that's parallel to the direction of wave energy. Now, the analogy and the example I'm going to use here is we're going to have a situation where we have some observers and we have a fire truck that is moving. Okay, so let's just label this diagram a little bit. Okay, so in this situation, your fire truck would be the source of a sound wave. And you have a couple of observers here. So we'll say O1 for observer 1, and we'll say O2 for observer number 2. Now, if the truck is at rest and the observers are not moving, both of these observers would hear a sound with the same pitch. So again, whatever the musical note is associated with the sound that's being emitted, both of them would hear the same pitch or same frequency. The analogy I like to use to explain this is pretend there's like some kind of like this like a launcher on top of like the fire truck. And what the fire truck's doing is it is just launching tennis balls in like both directions. So it's launching tennis balls towards the left and it's launching tennis balls towards the right. And maybe it's like launching like 2 tennis balls per second. Now, if you're standing here and you're the observer, whether you're observer 2 or observer 1, if that fire truck is at rest and it's launching tennis balls in both directions at the same rate, each observer is going to get pelted by those tennis balls at the same rate. So if the fire truck launched 2 tennis balls per second, observer 1 would get pelted as 2 tennis balls per second. If the fire truck emits 2 tennis balls per second towards the right, observer 2 be getting pelted by 2 tennis balls towards the right. Okay, so in this case, there's no relative motion between the source and the observer, and both of the observers are going to interpret the same pitch of sound. Now, let's say that the fire truck is moving towards the right. Okay, so once again, this is my source. And this is observer 1, and this is observer 2. Okay, and once again, we have my little machine on top of the fire truck that's just like launching tennis balls in both directions. Now, in this situation, because there is relative motion between the fire truck and the observers, there's going to be a different interpreted frequency. So between the source and observer 2, the truck is moving towards this observer. And this one is moving, the truck's moving away from that observer. Now, this machine is continuing to launch, for example, 2 tennis balls per second in each direction. Now, what would you expect to happen here? So if the truck is still launching tennis balls at 2 tennis balls per second in both directions, however, it is moving towards the right, which of these people do you think would be getting pelted with the tennis balls at a larger rate? Well, it should be observer number 2. The reason it's observer number 2 is when it's launching the tennis balls, as the truck's moving towards the right, there's a shorter distance for the tennis balls to cross. So observer 2 consequently gets pelted with those tennis balls at a larger rate. Observer 1 would be getting pelted at a lower rate because there's a larger distance for the tennis balls to cross because the truck is in motion. So the observed frequency for observer 1 would be less than the observed frequency for observer number 2. Therefore, the right side observer would hear the higher pitch, and the left side observer would hear the lower pitch. Okay, so that describes the Doppler effect qualitatively, and but we're going to look at this quantitatively as well. Okay, so what's the mathematical formula associated with this? Okay, so what we have is FO is equal to FS, V plus or minus VO, divided by V minus plus VS. Now we need to define these variables first. Okay, so first of all, FO, the O is making a reference to the observer. So FO would be the apparent frequency that is heard by the observer. And that's going to change. FO is going to change depending on whether there's relative motion towards or away from the source, or if there's no relative motion at all. Fs represents the actual frequency of the source. So that would be either the sound that's being emitted by the fire truck, or it'd be the light that's being emitted by that star. The observer would be those 2 people by the fire truck, or it would be the Doppler observing that star through his telescope on the Earth. V represents the speed of the sound, wave, and air. And again, usually somewhere around like room temperature, it's close to about 343 meters per second. VO is the speed of the observer. Okay, now this is where the equation gets, I'm gonna say a little more complicated, but not really, because we can actually just logically piece together how to use the equation. Okay, in front of VO, there is a plus or a minus sign. Now, you only are going to use one of them. It's either going to be plus or it's going to be minus. It depends on the situation. Okay, so let's say we have a scenario where the truck is moving towards the observer. Okay, so if the truck's moving towards the observer, what would I expect the observed frequency to be? Well, I would expect the observed frequency to be higher. I'm getting pelted more frequently by those tennis balls because they have a shorter distance to cross. Now look at the equation. What we need to do is we need to pick a plus or a minus that is going to make sense. So what selection, a plus or a minus, is going to result in a larger observed frequency? Well, to make the observed frequency larger, I need the numerator of the equation to be larger. So therefore, I would pick plus VO. On the other hand, if the truck is moving away from the observer, then I'm going to get pelted less frequently by those tennis balls. To have a smaller observed frequency, what sign would you need in front of VO? Well, I want the numerator to be smaller to make FO smaller. Therefore, you'd pick negative VO. Okay, so VO will select the positive if the truck is moving, or if the observer is moving towards the source, or negative if the observer is moving away from the source. Vs represents the speed of the source. Okay, now for this situation, again, we have to, like, in the equation, we've got to pick what makes sense here, the negative or the positive. Okay, so let's say that the source is moving towards the observer. The source is moving towards the observer, I'd expect the observed frequency to be larger. Now, what selection, a negative or a positive, is going to make the observed frequency bigger? Well, this Vs term is now in the denominator. If I can make the denominator smaller, I can actually make the fraction itself larger in value. So I'd want to pick the negative Vs. And on the other hand, if the truck is moving away from the, if the source is moving away from the observer would interpret a lower pitch. How do I get a lower pitch here? You need to make the denominator bigger. How do you make the denominator bigger? Plus Vs. Okay, so Vs would be negative if the source is moving towards the observer, or positive if it's moving away from the observer. So as long as you understand, like, whether the observed frequency is higher or lower depending on the relative motion, you can actually just logically and mathematically just piece together whether to select a positive or a negative. Now, there is one other thing. You might be wondering why on the top do I put plus minus, and then why on the bottom do you put minus plus? Well, here's the justification. Okay, well, let's do the top line. If this is plus, this means that the observer is moving towards the source. If the observer is moving towards the source, that will be the same thing as negative here, the source moving towards the observer. Okay, just think about it. So if the observer is moving towards the source, that's the same thing, relatively speaking, as the source moving towards the observer. Okay, so you can only ever have a combination of, like, plus and minus, or the opposite scenario would be if the observer is moving away from the source, relatively speaking, that's equivalent to the source moving away from the observer. So you either have plus minus or you have minus plus. Okay, so either the top two or the bottom two, depending on the situation. Okay, let's do a few examples here. So I have a fire truck moving at 15.0 meters per second east. So let's just identify some variables here. So the fire truck as the observer, or as the source, we'd say that Vs is equal to 15.0 meters per second. Okay, it has a 900 hertz siren turned on. So that would be the frequency of the source, 900 hertz. It tells me the speed of sound in air is 343 meters per second. That's just V with no subscript. And what we're going to do is we're going to calculate the observed frequency based on the following four scenarios. Okay, so let's start off here. Okay, the first one says that a person in a car, so that's the observer, is stationary. Okay, so let's write down our Doppler effect equation. So my Doppler effect equation would be FO is equal to Fs, and then I have V. Now I'm not gonna put the sign yet. We're gonna piece the sign together in a second. So I'll put VO over VS. Okay, and we'll logically put the sign in there.
Can you call 2403, please?
Okay, now first of all, it tells me the observer is not moving, so we can just get rid of this VO term. So that's gone. So we don't actually have to worry about a sign in front of VO. Now, how about the sign in front of VS? Is it positive or negative? Okay, well, it tells me here that the car is stationary, but the fire truck's moving away from it. So what happens to the observed frequency if the source is moving away? Well, it should be decreased. okay? Because there's that longer distance for the wave to cover. So how can I get a decreased observed frequency? What do I pick for a minus or a plus in front of Vs? To get a smaller observed frequency, I need to have a larger denominator. So I'm going to put the plus sign here. Okay, now we can just plug numbers in and calculate it. So this would be equal to the source frequency, which is 900 hertz. And then we're going to multiply this by V, which is 343 meters per second, divided by 343 meters per second. And then we're going to add 15.0 meters per second. And then that's going to give me, so even before we calculate this, we know that if there's relative motion away, that observed frequency needs to decrease. Let's see what this would be. 343 divided by 343 divided by 343 plus 15, multiplied by 900, and I get 862 hertz. Okay, so the observed frequency is lower because the relative motion is lower. Or sorry, the relative motion is in a manner in which the source and observer are moving away from each other. Okay, B says the observer is moving 15.0 meters per second towards the east. Okay, this one we don't actually need to do a calculation because here's what it tells me. It tells me the truck is moving 15.0 meters per second towards the east, and the observer is also moving 15.0 meters per second towards the east. Well, what's the relative motion between the two then? There is no relative motion. So I'd say since there is no relative motion, between the observer and source, it's like the observer and the source aren't moving at all. And if there's no motion at all between the two objects, then it just means that the observed frequency, FO, would be equal to the source frequency. So that would just be 900 hertz. Okay, so we don't actually need to go to the Doppler effect equation if there is no relative motion between the two. Okay, C says, okay, so now the person in the car is moving 15 meters per second west towards the truck. Okay, so let's start off with our Doppler effect equation. So I have FO is equal to FS, and then VO divided by VS. I'm intentionally just leaving the plus and minus sign out because we're going to piece it together. Okay, if there's relative motion where the observer and the source are moving towards each other, what would that do to the observed frequency? Well, if I'm moving towards the source, I'd be getting pelted by those tennis balls more frequently. So my observed frequency is going to go up. Okay, so how do I get an increased observed frequency? What do I need to put in front of VO? To get a higher observed frequency, I need the numerator to be larger. So I'd put the plus sign here. And I need the denominator to be smaller. So I put a negative sign in front of the VS term. Okay, so then we'll plug the numbers in. So this would be the source frequency is 900 hertz. We're going to multiply that by 343 meters per second plus the speed of the observer, which is 15.0. 15.0 meters per second. We're going to divide this all by 343 meters per second. Subtract 15.0 meters per second. And then I'm going to get an observed frequency We've already identified this needs to go up if there's relative motions, they're moving towards each other. So we'd have 343 plus 15 divided by 343 minus 15. We're going to multiply that by 900, and we get 982 hertz. So the observed frequency is higher because there is relative motion between the two where they're moving towards each other. Okay. And let's do part D. So now part D is the person in the car. The observer is actually moving away from the truck. Okay, let's do it on the next slide here. Okay. So D, let's write down our Doppler effect equations. We have FO would be equal to FS multiplied by VO over VS. Now, if there's relative motion so that we're moving away from the truck, I would expect the observed frequency to be lower. So how do I get a lower observed frequency? You need to make the numerator smaller and the denominator bigger. Okay, so negative in front of VO, plus in front of VS. So this would then be equal to 900 hertz multiplied by speed of sound and air, 343 meters per second. Subtract VO, and VO is 15.0 meters per second. Divide by 343 meters per second plus 15.0 meters per second. Okay, how would this compare, by the way, before we even calculate this? Let's make a prediction. Okay, how would the answer in A compare to B? So in A, the vehicle is stationary, the truck is moving away. In D, both of them are moving away. Well, if they're both moving away in part D, then there's an even larger distance for the sound across. So therefore, I should expect the observed frequency to be even lower in comparison to A. So let's see what happens here. So 343 minus 15, divide by 343 plus 15, multiply by 900, and I get 825 hertz. So yeah, it is lower. Okay, that's it for this lesson, and you can wrap up the course assignment-wise by completing the Doppler Effect worksheet. And for those who are done in Physics 20 regular, the course is over. For those in Physics 20 AP, there are a few other lessons dealing with rotational motion that we do also need to cover. So if you fall into that latter category, I will talk to you in those lessons.